second week of the climate change webinar. We're happy to have you all on board. This is a CARDI PPCR Climate Smart Agricultural webinar, and this is the second week that it has been on. I am Dwight Robinson, and I will be your moderator for today's session. We have two presenters that will join us today, and I will introduce them shortly. This session will continue. We will have another session tomorrow. I want to thank all those of you who were here last week and who have joined us again this week. And I want to give a special welcome to those who are joining us for the first time. And we hope we will see you tomorrow, and we will see you for the remaining sessions. The climate is changing, there's no doubt about it, and the only thing we can do is to adapt to this change to ensure we continue to survive through this process. So today we're gonna have presenters, two presenters, Dr. Simpson and Dr. Dale Rankin, who will present in the order I have named them. Presentation will be 20 minutes for each, but we want to hear from you. We want you to participate. And so we are gonna allow time after each present to have your questions. And so of course, you can post your question in the chat, or you can use the raise hand feature and let us hear your voice as you ask questions the presenters a little bit later on. We'll try our best to moderate and to ensure that we do the questions as they are asked to make sure you get your questions in. And so we're going to ask our presenters to, in order to make sure there's adequate time for you to participate, to keep their present, to try their best to stick within the 20-minute timeline given for presentation. I'll give a nudge because I know when you're presenting sometimes, you may forget, or you may be enjoying your what you're doing so much that you forget that we have a nudge at some stage if when the time has expired, and allow time to wrap up, because we want to have the audience participating fully. So thanks again for joining, and we're going to get right into it in the interest of time. So at this time, I would like to introduce to you our first presenter, and he's none other than Dr. Leslie Simpson. Dr. Simpson holds a PhD in agriculture from the University of the West Indies. He presently lectures in soil science at the Faculty of Agriculture and Forestry at the University of Guyana, and is also an agricultural and natural resources management consultant. He served in Jamaica as the CARDI representative for some time, and continued to educate himself by completing training in environment management at the Environmental Leadership Program at the University of California, Berkeley. He has co-authored several publications related to economics, and he maintains a very strong interest in matters pertaining to climate change and climate agriculture and agriculture in the Caribbean as it relates to climate change. I think you'll agree with me that he's well placed to speak to us today about the impact of climate change and how we need to adapt our soil and water management practices in this new era of climate change. Dr. Simpson, I welcome you. Over to you.
Thank you, Dwight. Let me just take some time to share my screen. I get it too. Now get it to go to the slide presentation for some reason. But if you're seeing it, we could perhaps go in this mode. This morning, I want to talk to you about soil and water management in agriculture. Now, climate change and natural hazards pose major threats to agricultural development in the Caribbean. These include drought, temperature increase, lower precipitation, sea level rise, and saltwater intrusion, increased intensity of cyclones, as well as shift in agricultural seasonalities. Climate change adaptation and resilience is therefore a key priority for agriculture sector development in the medium and long term in the Caribbean. The principles of climate smart agriculture, which encompass both adaptation to and mitigation of climate change, are generally recognized as the means to achieve sustainable goals in agriculture. The hazards already listed affect soil and water management for sustainable agricultural development in the region. This presentation provides how soil and water management practices in the Caribbean can be enhanced to ensure they fit within the principles of climate smart agriculture and the resources conservation category of compliance of the C-SAC model. From the climate change hazards we've mentioned, the following areas are specifically targeted in this presentation. And these are soil and water conservation, on-farm water storage, and soil water management. Soil and water conservation. Increased rainfall intensities and quantities associated with storms and hurricanes can enhance soil erosion, landslides, nutrient leaching on sloping lands, and cause flooding of the lowlands. There's therefore a need for soil and water conservation practices to reduce these risks. Soil erosion in the Caribbean. The nature of the topography, the erodibility of the soils, slope steepness, rainfall, and soil management practices can cause excessive soil erosion, which is a major factor in degradation of soils on hillsides in the Caribbean. Forms of erosion in the Caribbean are normally said to be sheet erosion, land slippage, and gully erosion. In fact, all forms of erosion, all the natural forms of erosion occur in the Caribbean. In Trinidad, Jamaica, and Barbados, substantial areas of steeply sloping lands are developed on shales. These soil types, land slips are also common. Other soil types, such as the shoal soils of Grenada and some locations of volcanic soils in Dominique, are also very erodible. Rainfall is another important factor in soil erosion in the Caribbean. And as I speak, rain is falling here in Ghana. Generally, rainfall quantities decrease from the windward to the leeward coast and increase with elevation. But it's not the total rainfall per se that is critical to soil erosion, but the intensity of the individual storms. And in the Caribbean, intensities of 25 to up to 125 millimeters per hour have been recorded. This is a slide showing you the types of erosion: splash, sheet erosion, gully erosion. This slide attempts to show some of the impacts of soil erosion. It has impacts on the soil resource itself and on the water resource. And the combined effect of these impacts is reduced overall crop productivity. Now let us look at soil and water conservation technologies. Soil and water conservation technology is developed from an understanding of the factors which have the greatest effect on erosion. Factors are considered to be rainfall intensity, called rainfall erosivity, the erodibility of the soil, the slope length and steepness, the type of soil cover and the crop type being grown, and any practice may be part of the system. Now, these factors were combined by Wishmeyer and Smith to form the universal equation, A equal RK LSCP, using the factors indicated above. And A is the mean annual soil loss, normally given in tons of soil per hectare per annum. But in terms of soil and water conservation, this is concerned with managing these factors to minimize the soil loss. These factors are influenced by soil management practices, which, first of all, decrease the effect of the impact of rainfall. So things like mulching and so on, which stops the direct impact of rainfall on the soil. Increased water infiltration, and the slower the water, the soil, the more it is able to infiltrate. Decreasing runoff. If you increase your infiltration, there'll be less runoff. And lessening soil movement. If there is trying to lessen it or to decrease it. Now, the principles involved in erosion control can be divided into direct control measures and indirect control measures. The direct control measures involve measures which aim at stopping or slowing down the erosion process. In the case of soil erosion caused by water, it is based on the following principles. Again, protecting the soil surface from the forces of the raindrop, and decreasing the speed or force of runoff, and intercepting the transported soil. Indirect erosion control involves such things as land use planning, which aims at using land in a way that prevents and or reduces the risk of erosion occurring. The other things like making them closed areas where no man-made activities are carried out. Now, erosion control practices fall into 4 main categories: agronomic, vegetative, structural, management, and a 5th, which is a combination of either 1, 2, or more of these management practices. I'll very briefly explain what these practices entail. Agronomic, these measures are undertaken within the cropping area for primary crop production purposes and includes practices such as intercropping, contour cultivation, minimum tillage, mulching, organic fertilization, etc. Sort of short-term measures need to be put in. Vegetative, these measures involve the deliberate planting of trees, shrubs, grasses, etc., or retention of areas of natural vegetation. Example, reforestation, contour hedgerows, natural vegetative strips. These tend to be there for more than 1 season, more permanent. And then there's structural, which is very permanent, which involves the construction of physical structures. For example, graded banks or bunds, contour stone lines, level bench terraces, artificial waterways, and drop structures. And then there's management. Uh, uh, and these measures arise from deliberate managerial decisions taken with the intention of protecting land from erosion. More the indirect methods of control. And I have here a chart done by Gums in 2001, attempts to give the types of measures that one would want to adopt in relation to slope. And you'll see that as you get steeper, the permanency of the structures or the measures increase. Let us move quickly on farm water storage and management. A notable climate change hazard, as we know, is increased periods of drought. And this has given rise to the development and use of on-farm water storage facilities, which facilitates irrigation of crops during the dry period. In general, these structures are safe, and the method utilizes water from 4 general sources: harvested rainwater, surface water, such as from rivers or streams, subsurface water, and recycled water. And I have some simple systems like this one, which just gives you a catchment area and a sunken tank. And then the other one where water is collected in concrete tanks from the roof of buildings. These are simple structures. And then we've moved now to more complicated or improved structures using heavy duty pond liners from which the water is moved from these by submersible solar pumps. The water is taken up into black plastic tanks by these solar pumps, from which the water can be distributed by pipes to drip irrigation and so on. There's also surface storage, and this picture shows you a surface storage facility in St. Lucia. It's formed by the damming of a river, of damming which allows more or less normal flow of the river until the dry season, when the water level may go below the actual dam. This is a controversial means of obtaining water and needs to be regulated to ensure that the farmers uphill and downhill get the benefits of the flow of water. Water recycling, this also includes the use of effluent, which is not very popular in the Caribbean, but popular in the Caribbean is moving drainage water into irrigation channels. It is practiced widely here in Guyana in our sugar industry. It means that you are using the water more than once before it actually goes back into the natural cycle. And so you're using, instead of using water once, you use it twice, the more efficient means of using the water. And then there's groundwater. Again, this one has to be regulated because over extraction can cause problems of salt intrusion and even further problems of salinization of your groundwater. And of course, once this water is collected, it is stored in the methods we saw just now. And here I have a summary of the methods as just described, and again, giving some indication of where the pros and cons of each of these methods and where they are practiced and so on. And then we come to soil water management. And here we're talking about the water which is already in the soil, which is there to provide moisture and nutrients to the plant. And again, this is needed because of the propensity to drought with climate change. So under these conditions, farmers develop technologies that can react to each of these contrasting situations, as well as exhibit the innovativeness needed to continue producing whatever situation develops. And I always use this picture because this is a farmer in St. Thomas in Jamaica who is planting what appears to be eddos in a little dugouts on a cambered bed, while on the top of the cambered bed, right next door, he has pineapples. And we know that pineapples love dry conditions, and we know that the dasheen or eddos need wet, very wet conditions. So he's decided that whether he has drought or flooding, he's going to get a crop. Now, water management is concerned with maintaining optimum levels of water in the plant rooting zone to ensure maximum performance. Besides irrigation practices, which will be covered in another lecture, soil water management involves many agronomic practices such as mulching, enhancing the soil organic matter content, and the use of biochar to ensure optimum soil water in the rooting zone. So soil mulching we all know about, and this is a picture of grass mulching, which is important as it reduces the evaporation of water from the soil surface. And we have a very unique situation, again in Jamaica, in South St. Elizabeth, where very low rainfall area, but it's one of the larger producing areas in agricultural production. And this is because it uses extensively a mulch system where the mulch is grown in situ, cut down, and the plants are planted in dugouts within the mulch. And then we also mentioned soil organic matter enhancement. And here we're showing that it is possible. It might be a little labor intensive, although there are machines that can be developed to apply organic manures. But to the plant, whole organic matter is applied, it's mixed up with the soil and the plant is added. Agroforestry systems, again, this is from Guyana, where in this alley cropping system, which is similar to a recycling system in the forestry, in forests. In this system, fast-growing species of Lucina and Lyricidia are planted between broad beds of field crops. And the large legumes, the Lucina and Lyricidia, are pruned at regular intervals during the growing season. And the clippings are used as organic mulch and to provide nutrients to the soil. This system also facilitates reduced tillage and is very effective, particularly in the lighter soils. And then there's soil carbon sequestration, which I've put as a heading because it encompasses a lot of the organic enhancement I just mentioned. So includes biochar, which is which we'll mention a little bit more about. Biochar or biocharcoal production and use in Ghana. As you know, biocharcoal, charcoal used in biological purposes, is formed from the carbonization of biomass. When it's applied to soil as an amendment, it provides the following benefits. It increases soil water holding capacity which is what we're talking about in this presentation. But it also increases soil nutrient retention. And of course, it increases the amount of carbon in the soil, which is carbon sequestration. And so it's taking carbon out of the atmosphere and putting it in the soil, which is of benefit, which is supposed to reduce climate change, or the greenhouse effect and climate change. There's therefore a heightening of interest in biochar use in Guyana over the last 10 years. I have 2 students working with me right now on biochar for their master's thesis. In conclusion, climate smart agriculture is not a new agricultural system, nor a set of new practices. It is a new approach to jointly address food security and climate change. Healthy soil and available water are vital for productivity in all kinds of terrestrial ecosystems, because plants require fertile soil to improve biophysical chemical properties and good quality of water for their growth and development. The use of soil water management technologies, as described in this presentation, is therefore imperative to reduce runoff, soil erosion, and to improve soil and water quality, moisture conservation, and overall crop productivity in a sustainable manner. This is my presentation. I thank you very much.
Thank you very much, Dr. Simpson, for that presentation. Now we can move to the stage where we can have our participants ask questions. So participants, it is now your turn to ask questions. Again, if you wish to speak, we can allow you, or moderator can allow you to speak if you wish to pose your question directly. If not, we have the chat where you can pose your questions in the chat and we'll ask it on your behalf, or you can pose your questions in the Q&A section as well. So we heard some of the challenges that we will face because of climate change, issues of intense rainfall, issues of not enough rainfall, and we heard a bit of how we could mitigate against some of these challenges. And so, I am sure you may have some questions that you'd like to pose to Dr. Simpson. So the floor is now open for you to pose your questions. All right, I'm seeing a question. It says, we have some rainwater harvesting ponds in Suriname, but we are seeking solutions to minimize evaporation of the water. What solutions can be applied?
All right, thank you for that question. In terms of evaporation, as in the soil, the only means of reducing evaporation is to cover. So it will mean having to provide some cover to the water storing facility. The other means is to minimize the amount in the open pond and to place more into tanks and so on, from which you are going to you're going to carry out your irrigation operations. The evaporation is a serious issue, along with other issues, but there is no way of it unless you can cover the water source. I hope this answers the question.
All right, I'm sure our participants will. And so I have a raised hand from VC Grace. VC Grace, would you go ahead and pose your question, please? You have, I think you could go ahead and unmute your mic and pose your question. Your mic is still muted, but you got permission to speak. PC Grace? All right, I'm gonna just, if you just allow me, if you're having a challenge with that, I would just move on. I'm seeing Josiah Noel. Josiah, would you go ahead with your question and we'll get back to VC Grace after.
Yes. Hello, good morning to everyone.
Morning.
So, to the panelists, I have a question in terms of what are the targets of implementing monitoring technology to really assess the effectiveness of the solutions and amendments we put. For example, using sensing technology. So it's one thing to cover to stop evaporation, also add nutrients to the soil. But what do you all see as the trajectory in terms of implementing actual smart monitoring technology so that we can measure our process and become a region that use more data analytics real time? Are there any provisions or intentions in implementing that into these systems? For example, real-time measurement of water quality, of water flow, water volume, the nutrients in the soil. For example, you spoke about the carbon sequestration, real-time monitoring of carbon in a particular area. So everything is not left to the human observation, but we can actually have hard facts and data that we can use for future analytics. Thank you.
Yeah, I think that's a very good question, very pertinent at this time. In terms of data, you know that we are a region that is has very little data to support our activities. My thought in terms of, first of all, the carbon you mentioned, the fact that carbon sequestration is important in terms of climate change and reducing greenhouse gases. I feel that we have to do more measurements of carbon or soil carbon to show that we are in fact doing sequestration, and we, in terms of carbon trading and so on, the farmers who do this type of work should get credits, monetary credits, because they've increased the carbon content of their soil. But I said, compared to the United States, where various new methodologies are being developed to determine carbon content and determine carbon content over while using the spatial data as well as a very good determination in the soil, just igniting the soil more or less to determine how much carbon is lost instead of going through laboratory processes and so on. So it is that kind of thing that I think you're referring to. And I am saying that I'm not sure where the plans and policies are, but I agree with you, that is the way we have to go if we are to benefit from the practices that we are advocating, or some of the practices I'm advocating here, particularly with respect to the use of biochar or the biochar. I'm not sure that I've covered your question, but these are my thoughts on the matter.
As I indicate, yeah, I think they probably follow up if we have. So I'm going to take two questions from the chat now just to keep it balanced. And so we have Mary asking, could biochar be helpful when planting trees? Or can any charcoal just be added to the whole?
Can biochar be helpful when planting?
Tree crops. Or could she just add any charcoal to the whole?
Well, I deliberately use biocharcoal in my presentation because a lot of the work that we're doing in field is using charcoal. And not biochar is prepared under specific temperatures and so on, and is thought to be more effective than charcoal, where because of higher temperatures you could get crystallization of the biomass and so on, or parts of the biomass, so that between the two, biochar is more efficient. But we are a biochar, we are a charcoal country, and we prepare a lot of charcoal. So it's easier to get charcoal, and it's cheaper to get charcoal than biochar. In terms of field crops, yes, we incorporate biochar or charcoal into the planting hole of the tree crop, and I have some formulations of planting hole mixtures which we use for different crops.
All right. Just a follow up on that one. Tony is saying that I would like to learn more as I'm now using biochar mixed with compost. Do you have any comments on that?
Yeah, yes, because biochar is a soil amendment that increases the retention of nutrients and moisture. It will not be effective if you don't add the nutrients for it to retain. And so the addition of organic nutrients as well as synthetic nutrients with biochar is where you get your best results. The nutrients, particularly the ones that are very solvent and easy to leach, are likely to be retained better in the presence of biochar.
All right. Okay. I'm just going to, in just time, I'm going to take two more questions from the chat, and then I recognize two questions, two hands raised, and I'll get to you very soon. So I just want to wrap up the chats, and this is the last set of questions I'll take from the chat, as we won't have any chance to come back here. So I noticed a comment from Francis Lopez indicating that windbreaks should help to reduce evaporation losses from ponds, but the trees also need water. I think that's a comment. Do you have anything you want to add to that, or just?
Yeah, well, that's an important comment. Using shade trees to help evaporation, and hopefully the trees are deep rooted enough that they're not affecting the stored water.
Okay. All right. Great. And just in the first question you responded from Iwan, where he accepts and thanks you for your response, but he just wondered if you had any suggestions for the type of cover, other than, of course, you just mentioned vegetative cover maybe, but and you mentioned that that's a possibility. Anything else?
Well, I was thinking of some physical uh, physical cover. You know, the cocoa growers have their sheds where they dry the cocoa, but they have a moving kind of thing with when the rain comes down, so they can quickly cover the cocoa. I was thinking of something like that, something that quickly covers the water, perhaps in the day, and then you can open it up in the night.
All right, good. That's something I guess we need to explore the different types of materials that we could use in the Caribbean to do that.
Right.
All right, great. All right. So we have a raise hand, Michael Gonzalez. Michael, go ahead with your question, please.
Hello, good day.
Good day. Yes, hearing you,
Um,
Michael.
Good.
Perfect. So I saw that the biocharcoal can increase the soil water holding capacity and the nutrient intake. I was just wondering how exactly it is able to do that, and if there's any data, like experimental data, not technology right now, about how a bigger percentile it can increase the nutrient growth or water uptake or crop growth in general.
Yeah. Well, there quite a bit of research coming out of the University of Guyana. Unfortunately, most of it is in pot studies, and they have indicated it. Well, in terms of scientific, it has the addition of biochar has been shown to increase nutrient uh, retention, and this is shown in the figures for the cation exchange capacity of the soil, which increases with the amount of biochar that you add. And of course, through moisture measurements, you can determine how much more it is holding moisture. And because it's doing these things, they've had increases in production of short-term food crops. We are now at the stage, and the two students I spoke about earlier, they are doing field studies. And I think these studies are going to give us a little more information on the rates. In the plant studies, rates of 20 to 30 tons of biochar have been found to give optimum kind of yields. In that 30 and 20, there's no significant difference between 30 and 20. But this could be due to root room and so on. In the field studies, I would expect that the optimum levels are going to be a little higher amount of charcoal that you have to think. But some of these studies I have and could make available to anyone who's interested. There are also some added things like microorganisms, the biological things in the soil being enhanced. It seems that some of these fungi and so on can use the pores in the biochar to proliferate better themselves from natural enemies and so on.
All right. Okay, thanks. So thank you very much. But just going, we have 30 seconds before the time expires, and we see someone wanting to know your views on plastic mulch. Could you just quickly give a comment on that, please?
Well, plastic mulch is just as good as the other mulch in terms of blocking, which is evaporating the moisture from the soil. The thing about plastic mulch, of course, the black mulch is going to carry up the temperature of the soil, and this may be detrimental to other things in the soil, the microbiological organisms, the actual plant roots and so on. I remember when I was in Jamaica, we had a trial there with different types of mulch. And this was actually as part of integrated pest management, where it's, I think it was that the reflecting mulch, you can have a reflecting mulch also, silver mulch, something that is reflecting. And this, it seems, tended to confuse the insects when they came to land on the plants. I'm not being scientific here. This is my take on what the entomologists were telling me about these silver mulches, these what I call artificial mulches that could be any color or texture and so on. So there are a lot of other uses besides evaporation for mulches. And so mulching, the practice appears to be an excellent one for various reasons.
All right. Okay. Thank you, Dr. Simpson, and participants. I apologize. In the interest of time, we have to move on. As you know, as we know, usually as discussion continues, you know, people get more involved. So I hope we'll be able to get those questions in as the series continue, or we may find a way for you to send your questions directly to our presenter, who may respond to you via email. So thank you very much, Dr. Simpson, for your presentation and for taking the time to respond to the questions posed by our participants. So now we're going to move on to our next presenter. And our next presenter is an applied climate scientist in the Department of Physics at the University of West Indies at Mona. He holds a PhD in and has worked on agricultural climate modeling research under the regional track of the pilot program for climate resilience project. He actually got his PhD with high commendation, which is not something that comes about very often. So you know the quality of the work he did. He's none other than Dr. Rankin, and his research interest is in climate and crop simulation modeling, more broadly assessing climate change impact on the socioeconomics of Jamaica and the wider Caribbean. Dr. Rankin is a member of the Climate Studies Group at Mona. And as you know, that group is a world leader in ensuring that the Caribbean has a voice in climate change and played a very important role in getting them to reduce the change to 1.5 instead of the 2 that they wanted, which you know would hurt the Caribbean, which is mainly island state. So Dr. Rankin has been doing pioneering research in climate variability and the impact on the agricultural sector. And I welcome him to speak to us in terms of the impact of climate change and how we can adapt to this. Dr. Rankin, over to you.
Thank you very much. Much appreciated, Dr. Robinson. Thank you so very much. I want to commend you on the excellent job you have done in facilitating the session. In fact, we really are deeply appreciative of that. Just to say that we are living in unprecedented times indeed, and it does take some time for us to get everything right, but we'll do our very best. I know I'm not supposed to ask, but just asking, can you see my screen, sir?
Yeah, we're seeing your screen now as your, not the presentation, but your computer screen with all the things.
All right, just a minute. All right, just let me know when you see it.
All right, your presentation has come up in a small window.
Is it okay now?
You're seeing it now, right? But I don't know if you can get it in presentation mode, as the last time we had some concerns. So.
Okay, let me see what I can do. All right, is it okay now, sir?
We're seeing presentation, just as we're seeing your next slide, you know.
But I think the problem is that I had a 2-monitor setup, which I'm trying to get.
Okay, all right, no problem. Well, you know, it's perfect. Okay. It's perfect now.
Thank you, sir. I appreciate it so very much. Okay, so today we heard an excellent presentation this morning. It dealt with some of the nuances of soil and water management. What I want to do over the course of the next 10 minutes, and I say 10 minutes because I have divided my presentation in two. The first 10 minutes I'm going to use to introduce a model that is a freeware, it's available online. And then the next 10 minutes, hopefully, if time allows, I'll try to do an application of the model, and hopefully it will pique your interest and you can take the time out at your leisure to go online and explore it a little bit more. I will say that this is quite a simple model, but it perhaps represents one of the best compromises between robustness and simplicity. So it gives really accurate results, but it is not as complex as other models that I've had to use. So what is the name of the model? It is called the FAO Accra Crop Model, and Accra in this case for water. Essentially what it is a model that allows you to see the response of the crop to water. This water could either be because of rainfall or irrigation or both. And it's an FAO model, as you've seen, and it really has a simulation for crops that have a known annual cycle called herbaceous crops. So crops like your potato, your dasheen, crops like your tomato and so on. So it doesn't do well for tree crops like mango and so on. And the reason it doesn't do, and there are not very many crop models that do well for that, is because when you're doing crop modeling, you have to do periodic sampling of the growth of the crop right throughout the life, from the first day you plant it to the last day you harvest it. So if you're talking about a mango tree, you could imagine a mango takes about 5 years to grow. At 4 years, when that tree is huge, you have to cut down everything of the tree and go and model it and dry the weight and all of that. That's very difficult. So most people don't do tree crops, they do herbaceous crops. It is important because it really looks at what happens when water is a key limiting factor. What do I mean by this? I mean that it assumes some basic things. One, that you're using modern cultivars, that there are no bad cultivars. It assumes that you don't have any major problem with pests and diseases. And of course, it also assumes that you're using the right amount of fertilizer. It makes these assumptions, obviously, because it's a simple model. There's another model that I use called DSAT, D-S-S-A-T, for just anybody who's interested. And that stands for Decision Support System for Agro-Technology Transfer. That has all of that fancy thing that can even mod the amount of money you can make and so on. But that has a way steeper learning curve. And it actually comes with a lot of data input. But this one is just a water one alone. What else can we say about DSAT? We can also say that this is what the interface looks like. When you go on the FAO website, and here's the link down here, www.fao.org/acrocrop/EN for English. It has a French version and an English version. It is there. It uses us, comparatively speaking, a small number of inputs. Now, why is this critical? Is because I just did a modeling of cassava in Jamaica, and I needed a total of 30 different parameters to model what one cultivar of cassava looks like. And I was doing 4 different varieties. So that is 30 times 4, right? That's 120 different parameters after tweak. With Accra Crop, it's a much smaller number of parameters. They're mostly icon-based, so it's a lot easier. As I said before, it's a good balance between robustness and simplicity. All right, so let me get you a little upset. So what it does, it actually tracks the development of the crop using what is called canopy cover, which is really using a digital camera. You take a photo of the canopy and you can analyze that. When we started the research in 2011, that everybody was using what they call area index, which is to go and then you get the area of the leaves, and that would be good punishment for somebody that gives a lot of trouble. And then you actually divide the area of the leaves by the area of the area that would cover. Now that is very, very difficult. If you went and you messed up, you'd have to go and get another harvest of leaves again. And of course, 1 minute after you harvest the leaves, it's not the same size. It has transpired, respired, all of those things. So a group of us in physics decided there had to be an easier way. So we developed a software called ACE, because we wanted to ACE it, called Automated Canopy Estimator, where you can actually upload your photos and it is independent of the type camera that you have. So there was another canopy software, and there were 8 other canopy software on the market, and we were able to prove beyond reasonable doubt that ours was the best. Not only because it was independent of the camera that you use, but also you could use a cell phone, you could store the images forever. When it does the segmentation, it actually shows it to 2 decimal places what it does. And also, what is also critical about the software as well, is that when you upload the images and you get back the data, you can actually see whether it is truly representative. Somebody came with what it does, it selects green, right? Even if part of the leaf is green and part is yellow, there's no other software that does that. And we also found that somebody brought some chicken on a plate with rice and peas, some callaloo, and some green vegetables. And the software was able to distinguish between the green vegetables and the callaloo and leave everything else. So it really does work. Now, why is this important? Because you want the canopy cover, you want what evapotranspiration you have. Now, this crazy figure down here, yes, I know somebody, but you don't need to worry about it. The model does all calculations. It assumes there's something called water productivity, which is how the crop assimilates starch, and it multiplies that by the amount of water that has transpired from the soil. When the plant opens to take in carbon dioxide, it loses water. So there's a very close nexus between respiration and water productivity. So the model has a simple way of saying, okay, multiply that water productivity figure by the amount of water that you lose, because that is very closely linked to the input of CO2 through the stomata. That gives you your total biomass. And then your yield is simply multiplying your biomass by your harvest index. And your harvest index is really your total weight, the weight of your tubers divided by your total. So it is the percentage of your, what we call marketable yield. So it's very suitable for the Caribbean, because most of the, and my friends from CARDI can tell you this, most of the countries around the Caribbean, and I've worked at the CIMH as well, and I did postdoc, most of the data needed for modeling is not available. In fact, they told us that we could not model cassava or any other crop in the Caribbean using the most sophisticated C-SAC model. Well, we proved them wrong. If you set up the experiment, you can. What do I mean by that? Here's what the interface looks like. When you start the model, this is what it looks like. If you are fluent in English, in French, like our good friend, Dr. Robbins, who's multilingual, you could also select German if you want. Here is the interface when you actually get ready to run the model. I'll explain each of these panels. The top panel here tells you the amount of transpiration that is taking place. If the plant is losing too much water, these blue bars turn into gray bars. You can stop the model, input water, and run the model again. This green bar tells you the canopy cover, whether it is maximized or not. If the canopy cover is maximized, then you will get better yield. Up here, it tells you your biomass. It tells you what your yield is. Your aim is to try and improve your biomass and your yield. Now, remember, because plants retain different levels of moisture, what the model does is simulates in dry mass only. So it dries everything into constant mass. So when I'm going to show an example, hopefully everybody can follow me. In that case, you could multiply this by like 3 or 4 times, because in some cases, dry mass is like 25% of fresh mass, all right? So, for this crop, and I'll show you what crop it is in just a while, you really have to think about your fresh mass. Now, the more sophisticated model I'm telling you about takes that pressure off you, because you can actually simulate in fresh mass. The bottom one now shows you what is happening subsurface. So field capacity, of course, this is what happens when you have excess water drained off. That is, what you really, really want. Permanent wilting point, of course, is when there's water in the soil profile, but the plant cannot access it. All right, so I have 1 minute and 12 seconds left for this part of the presentation. So let me just finish. So here's what happens. You have to set up your experiments. We had experiments set up at 4 locations. Rainiest area over here in the Pasley Gardens region that gets close to 5,000 millimeters per year. The driest location in Bodles, Ebony Park, that is a little wetter than Bodles, but still dry. And then probably the most ideal location for planting sweet potato. We did sweet potato. you look on this plot here, we had to label randomized complete blocks. We had 4 varieties, yellow belly. We had one called fire on land. We had one called uplifter. Presumably called so because it lifts people out of poverty. And then we had one called ganja. And I almost got into trouble because somebody went on the site and saw it and was willing to take a picture to say that UWI was farming ganja under the quiet. I had to explain to the minister when he saw it that this is the variety that we eat and not the one that we smoke. Okay, so here are the parameters. You get rainfall, temperature, relative humidity, solar radiation, and wind. These 1, 2, 3, 4, 5 parameters are used to calculate what we call evapotranspiration, using the A standard for evapotranspiration, which is a Penman-Monteith formula. You don't need to worry about how it does it. You give the model the values, and it will calculate it for you. All right, of course, it takes a canopy cover. And how the model works, it drags weather information, it's your evapotranspiration into soil evaporation and transpiration, because water lost directly from the soil to the atmosphere does not contribute to yield at all. So Aquacrop is saying, well, I don't care about yield, water loss that is not linked to yield. Let's split it. It then takes that, turns it into water productivity, turns that water productivity into biomass, uses harvest index to moderate this biomass, and then it gives you your yield. Very simple, all right, nicely explained, robust, accurate, yet simple. All right, as I said before, you don't have to learn any coding. Unlike other models, you just use a simple thing. What are some of the parameters that you need? You definitely need, the weights of your crops and so on. You need your harvest index, you need your planting date. It does not distinguish between different varieties of the same crop. So for example, when I was doing sweet potato, the mean, the answer mean of the 4 to say this is what. Some of the other models you can do that. You have to take your data at very, very regular time steps, sometimes monthly, sometimes every 10 days. If you want more accurate data, you have to take it more frequently. And then, of course, you have to look at your solutions. You must know your soil. If you can do a soil before you start planting, that is very to irrigate. All right, so what can we say about the model? It's freely available online. It's reasonably simple to use. It's very well documented. It's a very, very good user manual. And it can run climate change simulations, and it can simulate the yield response to water, the effect of irrigation schedules, and the effect of saline intrusion. All right, so what I want to do in the next 8 minutes of my time, I want us to look at an experiment. I don't know how many of you got the opportunity or the link from the hardworking Desi to download the model, but if not, I'll show you, you can always do it in your own time. And we are going to try to find for this experiment, what is the most suitable soil, what is the best irrigation schedule, best meaning most efficient and most economic, and also what are the effects of saline intrusion. That is to say, can we identify a crop that is salt tolerant? Okay. All right, so Mr. Chairman, with your permission, I'm going to share the interface, and you can let me know when you're seeing it, because I'm not sure what you're seeing. Are you seeing any interface, sir? Excellent. All right, so when you open the crop, when you go on the website, and if you just type in fao.org, this is what you will see. If you're not proficient like Dr. Robinson with all of these other languages, select English, please. All right, you click start. Just give me 1 second, sir. Let me just restart it. So while it comes back up, what I want to say is that most models that operate like this are not icon-based, all right? So you click start. The first thing you have to select is a climate. Now, if you're using the model for the first time and you go in and you say, Dale, I don't see anything related to Jamaica, that's because there's not a climate in Jamaica. Now, to teach you this is a 1-week course at minimum. So I'm not going to go through the teaching you how to select a climate file. I'm going to go to a file that is there. So if you have the model open, you go to select a climate called Brussels. All right. So we go to the top, look for Brussels. And when we select Brussels, all right, once you have made a selection, you always click main menu. You always click main menu. So it tells us that this crop has weather data. This site has weather data from 1976 to December 31, 2005. Next thing, you have to select a crop. In this case, because we're talking about root and tuber crops next, I'm going to select potato, all right? Now, let me explain something very quickly. Now, there are two potato crops here. There's a potato called potato default calendar, and there's a potato called GDD. GDD stands for growing degree days. When you use the GDD option, it takes effect that temperature has on the crop. So always select your GDD, all right? Once you've selected that, it asks you, when are you planting? I did some research and found that the best time to plant Irish potato in Brussels, in Belgium, is anytime between early spring to late summer. So the default date of the 22nd of March is okay. All right, so the next thing we know we have to select naturally is, and it's a very intuitive model, we have to select now the soil profile. Okay, so let's just select the soil profile. I don't know, well, I do know, but if I was doing a live session, I would ask somebody to tell me, or maybe I could do it, Mr. Chairman, with your permission. Can anybody type in the chat what soil type you think we should use? I'm going to show the soil types that are available. So we have clay loam, we have loam, we have sandy loam, we have paddy, we have sand. Anybody, can you type in the chat and tell me what soil do you think we should use? Whatever you say, I'm going to, Mr. Chairman, if you can.
Yeah, sandy loam has come up.
Sandy loam, okay, so let us use sandy loam, Mr. Chairman. So we use sandy loam. Remember, once you make a selection, you go back to menu. If you want to see what the sandy loam soil looks like, Mr. Chairman, you could click on display the soil characteristics, and you could click on it and you could see, for example, what is the total available water, what is the retention, what is the field capacity, all of those fancy things. If you wanted to create a soil of your own, you could also do it here, all right? But as I said before, this is a 1-week course, all right? All right, once you have done that, the very next thing now, it could ask you, can you tell us something about your groundwater quality? We are going to assume our groundwater is okay. Now it tells you you're planting on the 22nd of March. We told it that. It is saying based on your weather, you should be harvesting by the 27th of July. That is how good the model is. Right away, it can tell you. So the next thing you will do, so remember the first thing we did was select climate. The second thing we selected our crop. The third thing we selected our soil profile. Now, if after we run the model, I'm going to ask you if you got this, whether you would irrigate or not. I'm not going to tell you the answer. All right, so the next thing you go is you go to run. When you go to run, you click start, you can start and run it to the end of the simulation. So here we go, run. All right, remember what I told you about this little panel here? Anybody remember what I said about this panel? If you see gray bars, what does it mean? Can anybody tell me? Or type in the chat and say, if you see gray here, what does it mean? Anybody? Mr. Chairman, can you help me?
Yeah, I'm looking. I haven't seen a response yet.
Okay. So if we see gray bars here, what is it saying?
Somebody said more water.
Absolutely. You could also know, Mr. Chairman and participants, by looking down here. Remember, we said that this is field capacity, right? This is permanent wilting point. So this crop is dying because the water has gone way below permanent wilting point. So what you can do, there are a number of ways you can do it. And I'm going to show you a little way to cheat, morally, of course. All right, so what we're going to do, we're not going to run it to the end of the simulation. We're going to run it and stop it every 10 days. So we're going to repeat the run now. And we're taking our time. Once you see gray begin to appear, so we see a little gray here, we'll stop it, and you can put in like 50 millimeters right here. And then you run it. Remember the first time we ran it, we got 9 for yield, 9 for biomass, and we got something like, I think 6 for yield or something like that. So let's go, oops, see another thing again. We can put in another, let's put in 100 millimeters now. And then we continue, we see the crop recover, and we run it again, and we say, you know what, before we see gray, let us put in another 30 millimeters. We continue. And now we see that our yield, as our biomass has gone to 12, and our yield has gone to 9.3. So Mr. Chairman, what we had as our biomass, right, is now our yield, which means we have improved significantly. And if you multiply this by your dry weight for Irish potato is about 35–40%. You could multiply that figure by 2.5. So that is easy. One aspect here, we could still do better, right? That's it. Now, there are a number of things you can look at. So you say, okay, what does that mean? Well, if I go here, I can go to my environment. It tells me right what I used. If I go to here, when the plant matures, it tells me the amount of evaporation that took place. It tells me the amount of rainfall I had. So you saw the rainfall below. It tells me the total amount of irrigation that I use. All right. There are several other things that I could explore. I could show you how to experiment with salinity, for example, if we had time. I could also show you how to generate irrigation schedule without having to model any at all. But my time is up and I want to stick to it. So thank you very much.
All right. Thank you very much, Dr. Rankin, for that. I would say that you aced that presentation. You know, I always like when somebody presents and shows us way. Now, I'm gonna open for questions. This is a case of technology to adapt climate change, and I'm sure the participants have questions they would like to ask. So I'm gonna open the floor immediately. See already a question hand from Josiah. We're hearing you now. Go ahead. Oh, sorry. Yes, we were hearing you.
Are you all hearing me?
Continue.
Yes, okay, great. Yes, what I was saying is with the collective data from all the different users be collected and then analyzed, would data analytics also be involved in it, or it's just for the private user to be able to get some indicators of the performance of their assets? Or would there be like a curriculum analyzing all data? That's my question.
Okay, excellent question, Arch. Well, the two answers. The first one is that you have a local interface, but a global application. So that when I was completing research, I was able to share my parameters in the publication, and first time we're able to run the model anywhere in the sweet potato. Because once you calibrated it to your local conditions based on conditions, so it can be used anywhere in the world. That's the first part. Then is if I use my model and run sweet potato, and you are in Thailand, and you downloaded the model, would you automatically see sweet potato? And the answer is no. And it's very simple. It's simple because then your model is not messed up. But you can always interact with the author and say, can I get your parameters? Have a number of networks and multiple networks. I'm always willing to share. I've also asked, can you share your parameters with me? So in that regard, it can be shared. Sure that the integrity of the model is maintained, that nobody scrupulously goes and says they have created a crop that can grow on Mars that mess with yours, but the parameters can be shared.
Thanks very much. Okay, so I'm going to turn to a couple of questions in the chat. And we have a question from this that says there is a uh, it comes.
Not sure what it is.
All right. So this, could you just give some more information on the PPCR project? So we could determine if I guess things on specifics as to what it is that is being worked on. All right. So I move to the next question. How can the Caribbean start to work to create data templates for agrocrop so we do not have to use foreign ones?
Well, that's easy. What we need to do is do more field experiments, Mr. Chairman. Essentially, this is a way. When I started to do the modeling, the chief statistician at the ministry told me, good luck. There's nobody researching. One of my trials was 2 acres big. Nobody's going to take that. But I said, okay, fine. And for my PhD, some that's included 5 seasons of student labor from different institutions, and eventually a global contribution. Research, and let's use that as a means of applying it to the model. This model is very easy to use compared to some of the others that I have to use, right? And I think that can be done, Mr. Chairman.
All right, thank you very much. It's good, I mean, I guess you worked on this one and designed it with the Caribbean in mind, with the Caribbean focus. So you know what was best for us. All right, so moving on to a couple other questions. This one, see if you can get what you're getting at a little bit better than me. So it's just asking, what do we have in the Caribbean to test the weather and soil, and what would be the cost of such equipment?
So we have automatic weather stations now, Mr. Chairman, that are available. They can be used in a very cost-effective manner. The automatic weather stations, now you can get one typically for 3,000 US, something like that, or less, or $1,500 correction. The automatic weather station can give you up to 20 meters, so it gives you all you would need for any model in the world. But you can attach to that what is called a soil moisture probe. And if you like the presentation today, please have a video presentation to show you of something that was done in Jamaica. Every documentary, every video that is available prior to 2019 showcase people's installation in America. Or other way, we decided we were going to create content for Jamaica. So it shows you how you can use a weather probe for Jamaica. You attach it to the weather station and you can get the data, and it shows you how to irrigate and when to irrigate. The cost of the soil moisture probe is not expensive per se. I think $160 or something like that. But you can also get something called a tensiometer. And now that we mentioned that a tensiometer, Mr. Chairman, is essentially a glass tube that has a ceramic tip and it has a dial at the top. It operates on the premise that if you want to suck up moisture or even juice, for example, when you have a lot of juice in a glass, as you put your lips on the straw, the juice comes up. When the juice becomes less and less, you have to expend more energy. The principle operates the same thing for the plant. When there's a lot of water, the soil profile, the plant doesn't have to expend a lot of energy. But when there's a little bit of water, then it has to expend a lot of energy. So the higher the reading, the drier the soil. The lower the reading, the wetter the soil. Now that you can get for easy, $20, $30 online. You can get them at any farm store anywhere. The problem with that is manual. You have to physically go in the field to see it, right? You cannot automate it. There's a few of them that have been automated, but I wouldn't recommend them if you're doing high quality research. So there are options that are available, Mr. Chairman.
All right. Thanks very much. And I'm sure, the technology that you have tested and developed for Jamaica would most likely be applicable most places in the Caribbean.
Yes, sir. Yes, sir.
All right. Okay. So just following on that automation. So the other question, which is asking, can this data be exported and used with soil water potential sensors, which you just spoke about, for automatic adjustment of irrigation? So this person was asking, Kadeen was asking about, automating it. You mentioned that it may not work for research, but could that work for somebody who is just trying to cultivate?
Yes, Mr. Chairman, I will show all of that tomorrow.
You show that tomorrow. All right.
Yes.
So Kadeen, we guess you should be back tomorrow and you will get some more information on that. All right. Another question from Luciano. How many years of weather data is required to develop the most adequate model for a specific crop?
Ideally, the least amount of data that you need is at least 2 crop seasons worth of data, preferably in 2 different locations. And the reason they suggest that is that you can get a good year and get parameters, but then when a bad year comes, they're not as robust. So under normal circumstances, you need to get at least 2 years. I would also suggest that you get 2 different kinds of treatments. So if I was doing an experiment and money was not a limitation, I would do 2 years, and at each site I would do a rain-fed trial and a rain-fed plus irrigated trial. If I have all the money I need, I would do 3 years. So at least I have the minimum plus a buffer.
Okay, all right. All right. Now we have the follow-up question on, so PPCR, Parliamentary Integrated Climate Services Agriculture.
Okay, sure.
Okay. The University of Reading. You're familiar with it?
Okay, yeah.
Okay.
All right, so climate services, and in general, is if I can give you information that allows you to, it's similar to climate smart. If I can give you information that allows you to take advantage of the climate area, allows you to avoid the difficulty of the weather, would you pay me for the service? And the answer is for most farmers, yes. If you can tell them that drought is coming, you lose $10 million if you don't irrigate, but if you irrigate by X, you'll only lose $1 million. Any farmer that is worth his weight in salt to do it. So yes, it can be used. I have trained several people. I think I've probably trained more than probably 300 people already. And I've said this, Dr. Robinson. I told representatives, I said, this training always exceeds everybody, but it has a higher trend. Within 1 month of the training, less than 20% of you will ever look at it again. And nobody, I've never been even seminars like this, everybody goes back to their normal course of work, unless you have somebody who sits down and say, you know what, this is worth it. And so I became the John the Baptist, the person that said, well, those people that do marketing are not interested in agriculture and modeling, and those people that do modeling only do climate modeling. So I was morbidly curious and wanted to straddle both. But I'm 47, so I have started to download to some young 20-year-olds who are 10 times brighter than me. And we have, if I have time tomorrow, I will show you an app that we have created to any country, but at least to Jamaica. We have made it simple. You can click on a location of a crop that you want, and it can tell you what yield you can get. So it circumvents all of this that I just did, right? It's the latest craze. We're now trying to expand it. I think right now it has dasheen, cassava, and where is other crop? Dasheen, cassava, and pineapple. But it can expand to several other crops. Also, it can look at climate change simulations, sir. It can also look at what monetary loss. The minister saw it, everybody was excited, but of course they brought no money, which is a usual problem. But there are several options that exist, and if money is available, we can roll it out further.
All right. There's a lot of interest, So let me just quickly go through because we wrap on the half hour. Can the model be utilized for hydroponics?
In principle, yes. It's just that you'd have to get the soil, the properties. In terms of, instead of using the soil, when we were selecting soils, so we had sand loam and clay loam and all of that. You'd have to you'd have to create the profile for hydroponics inside. So you have a water medium in terms of a soil. It's not yet in the model. I would have to check with the FAO. I honestly have not seen it yet, but in principle, it may be able to work, but nobody has yet done that.
Okay, all right. And just going quickly, how do we further enhance the collaboration with the project and the app?
Well, that is left up to the PPCR. The project is almost finished. They funded me for 3.5 years. My contract ended in 2019, December. It's left up to them. I couldn't answer that question.
Okay, all right, great. Okay, we understand that. We accept your response on that. So a comment from David here says, I use aquacrop for climate change simulation. The challenge here is reliable historical data to test the model and projected data for future conditions, plus the field data. What's your comments on that?
All right, well, there's a very simple way to do that. We have a phrase in modeling says, all models are wrong, but some are useful. All right, so you will never get a perfect model, and you don't need to have a perfect model. I say, try to get decent. You don't need 30 years worth of data. You probably need, if you can get even 5 years of data. Make sure that the yield that you have is good. The problem is not the weather data, actually. The problem is the crop data. Because most of our crop data is crap, and that's the truth. Because we don't really have real weather data anywhere in the Caribbean, real crop data anywhere in the Caribbean. Most of the time, it's not differentiated by variety. So a Julie mango and an East Indian mango and a Blackie mango is the same mango, right? We don't differentiate by a variety, so you don't even know. And at the same location, we got 5 tons per hectare and 25 tons per hectare. So when you tell a farmer that the yield is 15 tons, it really doesn't tell him much. So the problem is not the weather data. The problem is having verifiable yield data. That is why we had to do our own farming. But if you can do even 2-3 years worth of data and get real data, you don't have a problem. Where the future is concerned, aquacrop, I think, is probably the best model for climate change simulation. Why? Because it allows you to input both the SRS scenarios and the representative concentration pathways. In other words, any climate scenario for the future, you can put it in the model. This is the best representation of how carbon is going to affect future yields.
All right. Okay, so
let me just quickly finish this. What happens is, because the model has a consistent error, once you are taking the future from the present and you take the percentage change, the error goes out and you look at the relative change. So you don't need to have a perfect model.
Okay, that's it. All right.
Yes.
Okay, all right. So just a final question and 20 seconds to respond to this one. A participant wants to know if there is any similar model for levels of agrochemical and fertilizers in soil.
There is the C-SAC model that I tell you about can work. There's a way to use it because you can utilize it. And in fact, it was FirstSun that actually came to me and said, since you can use the fertilizer and determine what is the best yield that you can actually get, I want to use your model. Because if I know that, I know when to optimize my production. And that is not even a crop model. That is just somebody who sees a business opportunity. So yes, models are there that exist.
All right. Okay, thank you. I want to apologize to Josiah. Based on the time, I will not be able to take the final question. I just want to thank you, Dr. Dale, for an excellent presentation and for the sort of interest you stimulated in terms of questions. As you can see, we're at the end of the session and there's still questions that want to be asked. But I know, knowing the person you are, you will make yourself available. Should anybody have any questions, they could send to you directly. And I want to remind you all that he'll be back tomorrow. And so you have a chance to listen in tomorrow and ask your questions again. Thank you very much. And I just want to take this opportunity now to thank, again, both our presenters, thank our hosts, and I want to thank you, the participants, for being here and for your involvement and the questions you have asked. And just remember, this continues. So we look forward to seeing you all tomorrow, and we look forward to seeing you next week. All the best. Enjoy the rest of your day, and we'll see you tomorrow. Thank you very much all.